Hi, this is a new video part of the research project Analog Spiking Neuron Model for Unsupervised STDP-based Learning in Neuromorphic Circuits. So this time I'm going to present the research project and I will try to be concise. So I do not need to present what are neuromorphic systems or unsupervised learning or STDP or encoding or whatever, because I already did that in previous videos. So I will provide the link in the description. And hence I will directly delve into the research project, and also a paper related to the project will be published soon in order to go deeper, because I will try to be concise here. So the aim of the project was to assess the impact of the random noise from analog spiking neurons on temporal learning rules such as STDP learning. So in fact, a neuromorphic system brings many benefits, but there are hurdles to tackle, and analog circuits present an intrinsic random noise due to transistor noise. So it can be flicker noise or thermal noise or shot noise, and so on. So this affects the precise spike timing, and this may influence the accuracy of analog spiking neuron networks using temporal learning methods such as STDP-based methods. So that's the steps I have done in my research project. So I will start by presenting how to model an analog neurons, analog electronic neurons, as part of spiking neural networks, considering the physical constraints. And because I've already presented, as I said just before, what is a synapses, what is a spiking neural network, how to encode the information, what is STDP, and stuff like that. So I will assume that you already know what it is, and all you have to know about the stuff. And thus I will directly go straight to the after presenting the modeling, I will directly go straight to the architecture of the spiking neural networks, and then the training algorithm of the spiking neural network, which is an unsupervised STDP-based learning algorithm. And I will briefly, but very briefly, present results on only the Github benchmark dataset, I think. So let's start. First, neurons stands for electronic neuron or analog neuron. And so here I will use a neuron from post-layout simulation results proposed by Pietro Ferra in 2021. So the analog neuron illustrated here is a Morris-Lecar neuron model. So this is a neuron model which starts to oscillate, like we can see here, after a certain amount of input current. So because we can't compute with a single neuron, I mean we can't train it and do machine learning stuff because it required at least a network. So we had to model the analog neuron in a software adapted to machine learning like Python, and then we can create a spiking neuron architecture by connecting multiple neurons. The model of neurons we've created, and then we can train and test it with some benchmark or whatever we want. So to accurately model an analog neuron behavior from analog circuit design, it's essential to incorporate at least 3 key properties from post-layout simulation results. So first, the dynamic of the membrane potential behavior over time is very. So this is illustrated by this graph. This is very important because this is what processes the information received. So it has multiple aspects that we have to include, like the threshold level, the resting potential, the reset potential, and the spike timing, and so on. So then the firing rates responds to different input. So this graph is also very important to include. This is kind of the transfer function of the neuron, and yeah. So this is the firing rate according to depending on the input excitation levels. Also very important. And another properties which is very important for analog neuron is the random noise from transistors. which is crucial for temporal learning, where noise affects the spike timing, and therefore the synaptic adjustment is also affected. So we can see here that the threshold level occurs at different potential, so it's not the spike timing is not regular, even if it's an oscillator. So yes, that's what we have to consider in the modeling of the neuron. So to model the electronic neuron, we have to pick a library. Since I'm more familiar with Python, I've only looked for Python libraries, but it must be equivalent in MATLAB or other languages, of course. So there is here plenty of libraries adapted for spiking neural networks. Some are more oriented to machine learning. They are based on Torch or TensorFlow. And some here are more oriented to neurophysiology. And here, what we want to do is, in the project, what we want to do is computation. So a library based on TensorFlow or Torch, like SpikeTorch or SNN Torch, would be more adapted at first sight. However, most of the time they do not offer much flexibility in choosing neuron models within spiking neural networks. So they are often limited to the very simple leaf neuron model. Whereas Brian2 is a very attractive library because it includes an ordinary differential equation solver, enabling to model whatever we want for neurons and for synapses. So it's very, very, very attractive for what we want to do, even if it's not really adapted. At first, I mean, it was not for machine learning, but it tries to broaden, and now it's even compatible to GPU, even if I still couldn't make it work. But on the paper, it's compatible to GPU, so very, very efficient for machine learning. And also, MNIST here should be very interesting because it's based on Torch library, and Torch is a well-known library for machine learning provided by Facebook. And it's well adapted to machine learning, and it does not include an ordinary differential equation solver, which is very useful for modeling neuron. But it is said, if we read the paper, so as in 2028, it is said that we can define the different equation of the neuron in the step function. So I haven't tried it yet, but it could be interesting too. And on the other hand, it's quite recent. It's quite a recent library, and there are still very few accessible open projects compared to Brian2, which is much more mature. So that's why we have chosen to use Brian2 waivers and MNIST. But yeah, MNIST could be interesting. So once we've picked the library, because it includes an ordinary differential equation solver, we can implement this set of equations and added a threshold function and a reset function in order to create our neuron model, modeling the analog neuron I've presented just before. So I will explain this set of equations in next slides. But what we obtain here is an activation function which is almost perfectly fitting the activation function of the neuron from post-layout simulation results. So the blue one here is the neuron we want to model, the activation of the neurons we want to model, and the green one is the model neuron we've created. So we can see here the linear error is almost always at the 0 level. And here, regarding to the membrane potential, what I call here the free segment model tends to fit quite well the blue curve, which is also the one from the post-layer simulation result of the neuron model. So we can now implement this architecture in a spiking neural network and trying to do a network, and so then train it and have some result on benchmark in order to assess the impact of the random noise. But I will explain it later, and now let's explain the set of equations. So here you might agree that this very simple equation depicts a linear curve right here, and by adding a threshold function and a reset function, it will provide a triangular signal. So this one. So the black one is the membrane potential of the neuron we want to model. So from the Morris-Lecar neuron, and the red one is a triangular signal. And in this equation, we can see that the input current here and the resistance membrane Rm is directly proportional to this slope, to the rate growth. So if we plot the activation function of this equation by including the threshold function and reset function, it will provide yes, an activation function which is a linear curve. So activation function, just remember, is the firing rate depending on the input current. Now, just by modulating the input current with an interpolation function, we can keep the triangular signal for the membrane potential, and we can modulate the activation function in order to fit perfectly the activation function of the neuron from post-layer simulation results. However, this equation does not include any leaky term, meaning that the input current, if the input current is cut off, the membrane potential would be constant, but it's not what we observe with simulation. The membrane potential tends to always go back to the resting potential. So we have to add a leaky term, because here it's only a very simple integrate and fire, and so we add here this leaky term, and in order to make the model, to implement the model with the behavior of the neuron to returning to its resting potential, always returning to its resting potential, even if there's no input current. Plus, according to MNIST in 1995, adding the leaky term leads to a better computational power by exploiting the decreasing segment of the excitatory postsynaptic potential. But now we can observe that the interpolation function does not fit anymore perfectly the activation function, because the leaky term just decreased the slope. So here in this equation, we still have the interpolation function and the leaky term, but we add an alpha term which enables to adjust the interpolation function affected by the leakage term. And now, here by segmenting the resistance membrane Rm, we can with this set of equations, we can fit much better the membrane potential. So here int is the function integer from Python. It's also called inversion brackets with a more mathematical aspect. So it's a function which returns 1 if the assertion inside is true, and it returns 0 if the assertion inside is false. Very simple function. Thus, the error of fitting with the membrane potential will decrease with the number of segments increasing. So yeah. Now, finally, as I said before, it's very crucial to consider the random noise from transistors, which could affect the efficiency when employing temporal learning methods. So even if it's, as we can see here, even if it's an oscillator, the time between spikes is not regular. So here there's an ideal neuron, Morris-Lecar neuron, with a regular time between spike, because it's a perfect oscillator. And here it's analog neuron, analog Morris-Lecar neuron, and even if it's they are at the same frequency, because there's free spike and free spikes, they do not have the same time between spikes. So here it's not regular, and that's how we define the noise in the analog neuron. So I'm not going to delve deeply into the noise modeling. More details are provided into the paper, and if you are interested in, you can also have a look at the theory provided by ADB in 2006. So the challenge here is that the standard deviation we observed in the random noise, this standard deviation of the random noise depends on some constants here, but also on some dynamic setting, like here the current of the synaptic currents, also the frequency of the spikes, and moreover, the more the neuron spike, the larger is the standard deviation. So there's kind of an accumulation of spike effect and effect, and this affect the random noise. Yeah, what we want to do here is to implement this set of equation into the previous model presented, and yeah, we can see that the noise is related here to the time, and so we can think of using the refractory aspect of neuron to do so. But sadly, refractory time can only be positive by definition, so it's a positive scalar, and which make it difficult to include a noise, because now the noise can be positive or negative, as we've seen. And so we've chosen to add the noise through the threshold level. So Brian2 enables to do such things very easily by adding a threshold equation with a random Gaussian term inside. And so we simply add this set of equations into the threshold function, and so now our model do check the three properties we wanted to add, and which are essential for modeling an analog neuron, as I said. So now, regarding to the spiking neural network, the architecture selection was optimized through multiple simulations on the XOR problem. So with different architecture, like with hidden layers or no hidden layers, with different number of neurons, or with different type of synapses, and with a winner take all or no winner take all, and stuff like that, and so on. So the input layer here, right here, is fully connected with the output layer. There's no hidden layer here. So it's fully connected with the output layer with both excitatory and inhibitory synapses, which are conducted by STDP. So the weights are adjusted with the STDP learning rule I've presented in a previous video. And here there's a lateral inhibition. In this lateral inhibition, the weights are constant, but they are randomly initialized. So they are not conducted by STDP. Because we use an unsupervised learning and soft winner take all with the lateral inhibition, we need at least to have as much output neurons as there are features in the dataset. So for the MNIST dataset, because there's 10 digits, we need at least 10 neurons on the output layer, and it's kind of the more the better. So the more neurons there is on the output layer, the better will be the soft winner take all. So winner take all creates a competitive learning to help neurons to specialize. It's often linked to unsupervised and CDP to help the clustering. And Mass in 2000. He explained in detail how winner take all works and how is it computationally powerful. And yeah, I will not go deeper inside. That's why I provide here the source. So regarding to the algorithm, I provide here the synthesis framework. So firstly, we start by creating the analog neuron model plus the synapses. And then we create the architecture just previously presented, and then there's the encoding method. So we used rate coding for the MNIST dataset. I will not present that. I've already presented in a previous video. So then what is important here is those three main functions. So training, labeling, and testing. Those are inspired from Jelen Cook in 2015. And yeah, so during the training process, weights are adjusted by STDP-based on the timing or spike between neurons. I mean the model of neurons. And in this phase, the network self-organizes without supervision or any reward. So each input data is processed during 120 microseconds, including 20 microseconds of resting time, allowing the variables to return to the resting values, preventing any neighboring effects. So following the training, a labeling process assigns meaningful labels to the neurons on the output layers. There's only one output layer, sorry. And this step is very crucial because it's essential for the evaluation of the network's performance in tasks requiring classification. So during the labeling, the activity for each neuron in the output layer is monitored as the network is exposed to 15% of the last inputs that were presenting during training. So each neuron is then labeled based on the input types that most frequently cause the neurons to fire. Finally, the network. We have to test the network in order to know if it's good or not. And so the network's performance are evaluated during the testing phase. And in this phase, new inputs are presented to the network, and the response of the output neurons is observed. So the response of the neurons is checked against the labels assigned during the labeling phase. So these three functions are repeatedly executed for a specified number of iterations, and there's also a criterion of stop. So if we reach for stopping, so if we reach a certain amount of accuracy, we just stop the training. And we can also see that there is the possibility in this algorithm to add different type of noise. So this is because the aim of the project was to assess the effect of noise on the spiking neural networks training, and so we can add different type of noise into the model of the electronic neurons, and this aids to study the impact of random noise on training and testing phase. So I'm sure you are already familiar with the MNIST benchmark, but just in case. This is a very standard benchmark for recognizing and classifying handwritten digits. It comprises 7,000 of images of digits ranging from 0 to 9 with a resolution of 28 by 28 pixels. Regarding to the results now, as I said, I will try to be briefly here. So with the very simple unsupervised learning algorithm depicted in the previous slides, the network achieved more than 50% of accuracy, which is not really good comparing to the state of the art, but still for an analog neurons, this is quite good. So it reaches over 60% during the training, but as I explained in the video about STDP learning, STDP alone can't provide an increasing accuracy during training. Because it doesn't guarantee an increasing accuracy during training, because nothing guaranteed the stay that the network will stay in local minimum, as it is the case with different algorithms like Adam or descent gradient descent algorithm. So we can see that the random noise from analog neurons significantly disrupt the learning phase when using unsupervised STDP method. So at least it's really disturbing for the complete neuron, the complete random noise of the analog neuron, because we can see that the red curve here never go higher than the random threshold level, which is 10% for the MNIST dataset. However, when the noise is neglected during the learning phase, and then the testing accuracy, so those three cases. In those three cases, the noise is neglecting during the training, but we add the noise for the testing part, the testing phase, And yeah, we can see here that the accuracy is only very slowly, slightly decreased when the noise is added after the training phase. So this encourages further investigations for more robust learning methods, because even if we add noise after random noise after the training, we see that the accuracy is only slightly decreased. But this can really affect the training phase. So I mean in this case. So as I said at the beginning, I wanted to be brief in this video. If you want more explanation, you can contact me on ResearchGate or read the paper. It will be published soon, and it will be open access. So if you're interested, you can contact me, or I will maybe do a video with more details. For now, I hope you've enjoyed the video and you've learned some stuff and you're interested in the subject. And yes, that's all for today.